of a completely decoupled system. So the characteristics that both equations need to be autonomous, meaning they depend only on themselves, right? So the derivative of x depends only on x, and the derivative of y depends only on y. No. No, you could have a +1 there, and it would still be partially decoupled. It would still be completely decoupled. Okay, what an example of a partially decoupled system? And dx dt is what? Yep. So one of your equations in your system to be partially decoupled, one of your equations has to be completely autonomous. The other one can be dependent on both the variables. Does not matter which one you make autonomous, either one. Yeah. All right, what's the first step of solving a partially decoupled system? Yeah, solve the autonomous part first. Because we have a handful of techniques right now that we can use to solve an autonomous equation. Okay, so for a single first order differential equation, in chapter 1, we developed 3 analytic techniques for solving it. So one was separation of variables, one was lucky guess, and one was integrating factor. And those analytic techniques are only applicable to equations of a very specific form. For a system of first order differential equations, there are even fewer analytic techniques, and they're even more limited. But we'll still study some of the ones that do exist because they can give us some insight into the behavior of other kinds of equations. And they can help us when we're studying qualitatively and quantitatively by checking that our solutions analytically actually match those techniques. So first, don't forget that even though finding solutions can be difficult, once you have a solution candidate, you can always check if it's really a solution, right? I had you do a couple of problems last class where I said, is this thing a solution to the system? So you can always check, and it's important to remember that sometimes we do a lot of crazy work in deriving the solution. Many of our techniques are just sophisticated guessing schemes, so it's important to remember that you can always go back and check if you actually found a solution. Okay, a decoupled system is one where the rate of change of one or more of the dependent variables depends only on its own value. Autonomous. So when that's the case, we can use techniques from chapter 1. So here we have a completely decoupled system. How would you solve this one? Yeah, so you can just solve each one separately by separation of variables. So if I've got dx dt is negative 2x, separation of variables, I bring the 1 over negative 2x to the left, dx, that equals dt, integrate both sides, and you're going to end up with x of t is ce to the negative 2t. Right, skipping all of the integration in algebra because we've done similar problems a bunch of times. Yeah, and then we're going to have y of t is going to end up some other constant ke to the negative t. Yeah, then you use your initial conditions to solve for c and for k. So y of 0 would be ke to the 0, which is 1. So k is 1. So I know my y of t is just e to the negative t. That's one of my functions. And then my x of t, x of 0 is also 1. So c has to be 1 also. So x of t is e to the negative 2t. It does check. Good. And just to get in the habit of writing these things in vector notation, you could either say xy equals e to the negative t, e to the negative 2t. That's another way of expressing that same thing. Or you could say, often we call it y. Y represents a vector xy, bold y. Yep. None of these notations is any better than the others. I'm just kind of showing you all of them in case you see it. Oh, I switched them. Sorry. Thanks. There we go. All right, so that seems okay, right? We're just doing the same thing we did in chapter 1, but now because we have a system, you have two answers, an x of t and a y of t. Okay, so here's what happens when you have a partially decoupled system. One of these is easy to solve. You can solve it on its own using separation of variables, the y one, right? If y prime is negative 4y, what's my function y of t? K e to the negative 4t. And you could get there by separation of variables, or maybe you just recognize that that's the solution because we've done it a bunch of times. Okay, so I now know what y of t is. So in my dx dt equation, I'm going to replace the y with k e to the negative 4t. Now this has that special form. This is a linear differential equation because it's linear in the dependent variable x. And we have two methods. We could either use lucky guess or we could use integrating factor. Any integrating factor? Okay, so for an integrating factor, we move the 2x over, right? So you're going to have dx dt minus 2x is 3k e to the negative 4t. And the first step of integrating factor is to find an integrating factor, right? So step 1 is to calculate mu of t, which is e to the integral of what? G of t, and what is g of t? Yeah, in this case, it's negative 2. It's whatever is attached to the x. Yeah. So this is going to be negative 2 dt. So this is e to the negative 2t. So that's my integrating factor. And I don't need the plus c when you're doing an integrating factor. You can drop it. And you multiply both sides by the integrating factor. Okay, so on the left, I have e to the negative 2t times dx dt minus 2x e to the negative 2t. And e to the negative 4t times e to the negative 2t, what is that? E to the negative 6t. Like bases, add the exponents. Okay, over here, I have e to the negative 2t times the derivative of x minus x times negative 2 e to the negative 2t, which is the derivative of e to the negative 2t. So what I've written here, that is the result of applying the product rule to x and e to the negative 2t. And then I integrate, and over here I get x e to the negative 2t. And over here, 3k is just a constant. So the antiderivative of e to the negative 6t is going to be negative 1/6, negative 1/2 k e to the negative 6t. Yeah. Thank you. Plus c. And then the very last thing, divide both sides by e to the negative 2t to get x by itself. So e to the negative 6t over e to the negative 2t would be negative 4t, right? This would be negative 1/2 k e to the negative 4t plus c over e to the negative 2t. Same thing, yep. You could also do, yeah, I have a negative, yeah. Yeah, so I could, that actually was probably simpler though. C e to the 2t. Move the crying baby up. No, no, this is Linda. That's Linda's memory thing that she uses about the negative x. Okay. Anyways, so now I have a formula for x and a formula for y that I found way back here. Oh, that is the same k, yes, because I put that k. That k came from there, because this was a 3y, and I replaced the y with k e to the negative 4t. Same k, yep. But I do have two unknown constants. I've got a k and I've got a c. I have to figure out both of them, and I can use my initial conditions to get them. So I know that y of 0, y is the easier one. Y of t is k e to the negative 4t, and y of 0 is k, which is 1. And then x of 0 is going to be negative 1/2 k, which is 1, plus c, and that's all 0. So that means c has to be a half. And then my answer, I have to actually rewrite out the functions, replacing the c's and the k's with the numbers. Okay, so x is negative 1/2 e to the negative 4t plus 1/2 e to the 2t, and y is e to the negative 4t. So there's my explicit solution. No, not at all. Nope. I'm just trying to get you used to seeing both, because we're going to start pulling in more and more vector and matrix notation as the semester goes on. Yep. This is a particular solution that corresponds to a given initial condition. Yeah. The ones we found up here were the general solution. All right, I'm going to encourage you when you're doing your activities we just reviewed integrating factor. Try to do at least one of the problems I gave you with lucky guess, just to keep it fresh, because we're going to come back to both of them in future classes. So, I think that's